Nice pleasure to have today Andrea Maselli from GSSI. So let me introduce first Andrea briefly. Andrea got his master degree in compact biometers at La Sapienza, and then his PhD always at La Sapienza in tidal interactions in compact binaries. Then he moved around Europe for some postdoc in UK, USA, Germany, and Portugal. And then he moved back to Italy, to Rome as a postdoc and then assistant professor. Then he moved finally at the GSSI in 2020. He got the position as an assistant professor too. And then from last year, he is an associate professor at GSSI. So today, Andrea will talk about matter of law, right?
Yes. Okay, so, thanks for the introduction, also for the kind invitation. It's actually my second time in an observatory, and because I'm not really an astrophysicist by training, but it's always fascinating. I mean, it's the first time was in Rome. It's actually PhD school, so like 15, 20 years ago. And so I've decided to talk a bit of something which goes to my past a bit, in the sense that this is not my currently super theoretical work, but I think this may be interesting for a lot of aspects, and it's a fancy, actually it's a topic that like recently, and I'll explain you why, became matter of a lot of fancy titles on the archive, because there was something related to this lob, and physicists, especially theoretical physicists with absolutely no imagination, start putting on the archive a lot of very ambiguous titles on the archive with this lob meaning them. Okay, I just want to give you a brief motivation. I'm going to be talking mostly about neutron stars and the internal composition of the neutron star. You may be wondering why. I mean, the answer is always kind of clear, but it's also very good to reiterate this. It's because there is a plethora of data that is coming. I mean, of course, there are like gravitational wave observatories, although we have not been let's say, not lucky, but in a sense, we had only one event, let's say 1 event and a half. The second was not very informative for the things that I'm going to explain. But of course, I mean, we have like a new window onto neutron stars. There are like, besides the data that are coming, there is the Einstein telescope, Cosmic Explorer, but also there are a plethora of observatories in the electromagnetic bands. So there are new satellites, and actually also current satellites, which are making like spectacular measurements of pulsars. So there are new data, and this data, I mean, also because of the increase of sensitivity of accuracy, can actually allow in general to I say they put at test the nature of compact objects. So either black holes or neutron star, or I'll try to pinpoint just at the end of the talk even something more exotic. So there are a lot of legit questions that you may ask when you have this data. One of these is what's inside like stellar cores, and in particular like neutron stars. Okay, what is the internal composition of neutron stars? So the science case that I want to talk about are mostly, okay, this of course it does not reflect here. So mostly it's like the nature of what is called like the dense matter, okay, at supernuclear density. And then because of this subtle word law, I just want to tell you something that we can do with neutron stars and with binary neutron star observation, also for test of gravity, and to distinguish some more exotic scenarios that have been proposed and are quite mainstream in literature. Okay, I will mostly talk about gravitational wave binary sources and signals, but I mean, I will make a contact also with the multi-messenger observation, which is like a sort of golden series of words now. Okay, basically, if you want to like to highlight the neutron stars in terms of science case, at least for the relevance of its internal composition, this is probably one of the key plots that you can show. This is basically a phase diagram for like dense state of matters. It's basically temperature versus, if you wish, like density on the x-axis, and there are on top drawn different experiments and different states of matter. For example, you can see at the low density and high temperature the LHCs. There are different phases of matter like quark-gluon plasma, the other standard hadronic matter. And I think the key point is that there is this angle here, which is sampled by neutron stars, which is the low temperature and the high density regimes, that tells you basically that a neutron star like occupy a space in this phase diagram at high density, which in general don't intersect with other experiments, and which is peculiar to a particular state, this one of superfluid or color superconducting phases in general, is the high density such that we can have new degrees of freedom appearing in the state of matter, like the confined quarks or like particular state of matter that I'm gonna elaborate in a while. So there is a specific region which only belongs to neutron stars. Now, I think that when I was PhD, I started doing that, saying that with neutron star you can do things that are difficult or hardly reproducible on Earth. Of course, there are experiments like iron collisions or other kind of experiment that can help understanding what is happening, or like at densities which are typical or like order of magnitude neutron star cores. But still, observation, astrophysical observation of neutron star are really the key to probe this high density regime. Now, what is this high density regime in terms of a quantitative statement? This is like an onion shape or an onion representation of neutron star, just to understand what's going on. And so basically how we think that neutron stars are modeled from the outest crust to the inner crust. So at least up to, and I'm going to explain you about up to the outer core, more or less there is a general consensus among astrophysicists and mostly nuclear physicists on what's going on in a neutron star. So the outer crust is mostly given, or thought to be given basically by a gas of electron into a lattice of nuclei. Then you have the inner crust, in which basically you increase with the density. And a good friend of mine told me that probably an Italian made this kind of classification, but basically if you increase of the density, there is a rearrangement of like the internal structure in a series of structures that have been called like pasta phases, because of some called like clear structure. So you go from this spherical shape gnocchi to the like more elongated backwards. I mean, and then that mutates into lasagna shape. So there are basically the equilibrium just given by this kind of rearrangement. And then there is the outer core, which should be basically given by a gas of neutrons, protons, and electrons in beta equilibrium. At some point, basically, the density becomes so large that it becomes favorable to produce with beta decay muons. Okay, so you may also have like muons. And more or less, that's basically it, in the sense that there is also a large part of the neutron star, which is the inner core, in which basically we lose control. And we lose control because basically these regimes here, so the outer core, more or less arrives at this value rho naught, which is called the nuclear saturation density, okay? So what is inside between 2 and let's say 10 times the nuclear saturation density becomes a bit matter of extrapolation and speculation, because we don't have theoretical models that predict what's going on. There are different, I'm going to tell you what an equation of state means, but there are different models that try to model basically, or to describe how the interaction modify the structure of the inner core. But here, depending on the particle content and on the way that you model this inner core, you may have different things going on, like phase transition. You can have the appearance of hyperons, in which there is like this change of quark nature, condensate, like meson condensate, or like quark deconfinement. So basically, the density can be so large that at some point you basically have free quarks inside. And this, of course, changes the properties of the overall structure and its macroscopic observables. And the key point is that, as you see, basically, if you are able to understand what's inside the neutron star, in particular in your inner core, you may be able to say things or put constraints on the state of matter at supranuclear density, so which can be up to 10 times the nuclear saturation points. Okay, this is a lot, and this is very difficult to reproduce, if not impossible, with terrestrial experiments. Okay, or at least in which way or how this uncertainty that we have in the inner part of the neutron star translates physically. This uncertainty basically becomes this kind of thing when you want to plot, because the variety of equation of state, or the variety of models that we use to describe the internal composition basically turn into a variety of the equation of state. Now, without going too much into the nomenclature, an equation of state, or at least a barotropic equation of state, is basically a microphysical relation that relates two things, which are the pressure of and the energy density inside the star. And basically, different models that were supposed to describe the last triangle of the neutron star onion becomes this. Okay, so each of these colors basically provides a different equation of state, which basically means a different internal composition in the inner core. Now, the name doesn't really matter, but just to tell you, for example, that some of these means like that you have an inner core in which you have hyperons or kaons, or in which up to the inner core you only have like neutron, proton, electron, matter, or you have like the basically stars with strange quark which are inside. So all that variety of our theoretical description becomes, okay. This is still a bit difficult to visualize, in the sense that this is still like, again, something macrophysical, but this thing, which what in general I call like the micro view on the equation of state, then becomes the macro view. Okay, so that, so if you want to follow like a logical process, the uncertainty that you have in the theoretical model becomes an uncertainty and a spread in the equation of state, and then this becomes an uncertainty and a spread in the macroscopic observable. So the things that we constrain with astrophysical observation, and in particular, like for decades, our principle or the main observables from neutron star physics was basically the mass and the radius. Okay, and this is indeed a plot, a mass radius diagram, in which again each of these curves basically represents one of the previous equation of state. Okay, that well, predict different stellar families, and there are basically different constraints, theoretical constraints. This gray line here, but here you see also this horizontal constraint, which is given by the observation of the most massive pulsar of 2.3 solar massive, whatever that we got so far. I think NICER put a measurement of that star. And basically, if you believe that there is only one equation of state regulating all neutron stars in the universe, your equation of state should also basically be able to satisfy this constraint. Okay, so the maximum one constraint. And so basically, the game here so far was, okay, you make a measurement of the radius. In general, that's the most difficult part. You make a measurement of the mass. You see basically where the two things intersect. And more or less, I don't want to say you try to identify the equation of state, but at least, I mean, you try to rule out models which are not astrophysically viable. Okay. And there is like this plot also highlights something which is very, very peculiar of the models with which we measure neutron stars, is that not only in general, I think astrophysically, like from an observational point of view, it's difficult to make a measurement of the radius, but also if you make a measurement of the radius, it's also very difficult to constrain the equation of state, because if you see like the variation in the mass, the ratio, the radius profile is almost vertical. Okay, so there is almost a complete degeneracy in the mass between the masses and the radii. So it's very, very difficult when you measure that to identify. Indeed, I mean, probably the best thing to isolate one of these, to make a lot of measurements of neutron star masses, possibly spread out like in very different places, from the most massive to the least massive, in order basically try to reconstruct as much as you can the slope of this curve. Okay, far from when the slope is almost vertical, so almost completely degenerate. Okay, so the equation of state is basically what is called like the holy grail, okay, of nuclear astrophysics, because there is a sort of interplay. You don't know the equation of state, but the equation of state affects and influences a lot of fundamental physics and physics on neutron stars. Okay, so this uncertainty is not only because you don't know the structure. A lot of magnetic fields, the way that they actually the binary evolves, I mean, depends on what you put inside neutron stars. There is, again, this problem, and in general, as I told you, the way to identify which of this model was more likely to describe the state of matter inside a core was this, what I call like from micro to macro, or from macro to micro. So try to constrain like mass, radius. Later, there's also like the moment of inertia of a neutron star, which apparently is one of the most difficult things to measure. But I mean, they provide a measure, I think, last year or 2 years ago. And you could do this with the low mass X-ray binaries, laboratory experiment, pulsars, and so on. Okay, the new thing that happened in GP17, 2017 was that together with the usual channel of the electromagnetic side, there also were gravitational waves from binary neutron star that basically allow to give a complementary view on this from macro to micro problem. So try to understand from the evolution of compact binaries, which is the state of matter which is inside neutron stars. Okay, and how do we do this kind of map with gravitational waves? That this is where LOVE comes into game. Now, LOVES is not again. I mean, besides like the ambiguities, because of this. I think it was a geophysicist from, he wrote the first article in 1908, okay, a British geophysicist, I guess, and, or in any case, let's say an astrophysicist that was working on studying tidal forces of planets, and I think like basically, yeah, planets, or in any case, in the solar system, okay, and this is like the original, the original paper. And from Sir LOVE, I mean, this astrophysicist, we now got what has been generalized in general relativity and blah, 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 but what is called the theory of LOVE numbers. So what are these LOVE numbers? It's actually something extremely common. It basically is a set of numbers, and I'm going to just tell you about one, the principle of numbers that I'm going to just call LOVE numbers, that will tell you how an object deforms when it's subject to tidal effects. Okay, so again, it's basically something that you will experience every day with the moon, and it's basically this guy was actually studying at the time what was happening to a planet when there is like a tidal source, a tidal field given by a bigger planet or by the sun that is actually deforming the small planet, the small object. And a way to characterize the deformation is through a set of numbers which are called the LOVE numbers. Now, in general relativity, there is a very nice and simple equation too, and this is the only equation probably I'm going to show, that basically tells you how these LOVE numbers connect with the property of the object that is deformed by this tidal field. Okay, and this is basically this equation here. Now, just to tell, the real LOVE number is K2, okay? Lambda is the tidal deformability, but I'm going to call the like K2 or lambda LOVE number the same, is basically the same thing. And if you see, basically, these are the constant of proportionality between two things. This is the external tidal field, and this is the star quadrupole tensor. So basically, this is the source of deformation. So EIJ is the tidal force that is actually deforming the object. Q, the star's quadrupole, is basically something that tells you how much and in which way the star deforms. Okay, this is the coupling of proportionality. Okay, so the LOVE number basically gives you the magnitude of these deformations, which are sourced by E and are basically specified in which direction, in which amount by Q. Okay. Now, the point is that these LOVE numbers just depend on the equation of state. Okay, so basically it encodes the property of the internal composition of a planet, of a star, or whatever is subject to the tidal force, and actually basically depends only on the compactness of the object. I'm going to explain you later. And crucially, these LOVE numbers, lambda, enter into the gravitational wave signal, and I'll show you a slide. So basically, as the masses of the spin of a binary neutron star, that's another parameter that characterizes the binary evolution and the gravitational wave emission. So if you can, the gain basically is that you have an extra parameter in the signal, you can measure it, and since this parameter depends on the equation of state, you can now play the same game that you were playing with the radius, but with an extra parameter. I'll show you some examples. Okay, and just to give you like an idea of what's happening, so this is basically what you see here, this is the signal given by two classes of sources. The black line is like the signal that you would get from a binary black hole event. And then like these colored fancy lines here are the gravitational signal that you will get from neutron stars with different internal composition. So from different equational state labeled by basically this label here. Okay. Now, if you see basically, and okay, this is like the Virgo curve. Now, regardless of where they lie on top of the, or below the Virgo curve, but basically there is like there are three stages that you can see that far from the spirals. Basically, there's no difference between the binary black hole and the colored neutron star curves, which basically means that the binary neutron star literally behave like point particle, like black holes. Okay, so they are far apart. They are very low frequency. Low frequency means they are very far separated. So basically, the signal doesn't know whether they are nothing else but point particles. Okay, so they could be everything. Nobody knows. But when you get closer to the merger, so at higher frequency, there is something popping out, and this popping out is Seidan forces. So the stars are getting deformed, and the deformation depends on what you put inside the star, because different type of equational states or different form of matter produce different signal, because I mean they depend on whether there is food, plastic, or nuclear matter. Okay, and then deviates from the binary black hole line. Okay, then there is the ring down, because there is oscillation that as well, depending, let's say, more chaotic way from the matter composition. Now, in general, well, the equational states are classified, regardless of the log numbers or the radius, into stiffness, okay? So very soft and very stiff means that if you have a neutron star with a certain mass, let's say 1.4 solar masses, soft means small radius, stiff means large radii, okay? So a stiff equational state gives you larger radii for a given mass. Now, for a given mass, larger radii means also lower density, okay? Now, if something is lower in density, it's also more easily to deform, okay? Something which is very, very compact is difficult to deform, okay? Which also means that a soft EOS, which means larger density, so more compact, since it's more difficult to deform, means smaller log numbers, because the log numbers tell you how much things deform. So if it deforms little, basically the log numbers are very small. Stiff equational state instead are smaller densities, because stars are fluffier, okay, which means that it's easier to deform it, and so the log numbers are larger. All right, so this also means larger effect into the signal. Okay, and then basically having the log numbers duplicate or actually makes the game of selecting the equational states more powerful, because up to the gravitational waves observation, we only have this plot here, the left-hand side, so the mass and the radius. This is basically, again, the mass-radius curves. Now we have a mass log number curve, and together with putting a vertical band and a horizontal band here, you can also put a vertical band and a horizontal band here, and try to see whether the two things basically are complementary, okay? Now here, I'm also giving you 3 results, that some of which have been actually studied or obtained recently in literature. And so these two actually belong to probably the topic that I won't be able to cover by time, which is how we could use actually log numbers to make tests of gravity. And this is because for neutron stars, which have a compactness between 0.1 and 0.2, depending on the equational state, the log number is different from 0, and is of the order of 10 to 4. It's actually a big number, okay? But there is some theoretical calculation that show you that if you take a black hole in general relativity, the log number is equal to 0, mathematically, okay? You can put it to 0. But there are other objects, for example, black hole in theories of gravity which are not GR, or like some proposed exotic compact object, I'll tell you later if I have time, which have log number different from 0, okay? And this has become a super powerful tool, also adopted by Lago and Virgo, to make tests of gravity or of the nature of black holes. As Fulvio Ricci, my professor of thermodynamics, was saying, like during the courses, like 0 is the best point to move from for a physicist, And basically the idea, for example, to make this thing for a test of gravity is that if you imagine like to observe like let's say 200 solar masses black holes or 200 solar masses compact objects, okay? And by chance, you are super sure that you have measured a log number different from 0. You either haven't understood anything about stellar evolution, so there are stars of 100 solar masses, or there is something else which is not a black hole. This is basically the rough idea of how to use this as a test of GR, but I'll talk later if I have time. Okay, and basically this, in terms of stiffness of the equational state, again, this was the classification that I gave you before. So for a fixed mass, so let's say 1.4 solar mass, for example, larger radii means stiff equational state, smaller radii means soft equational state. Okay, where do I find the log number? I find the log number in the gravitational waveform, and indeed, basically, if you have like the gravitational waveform that you detect with LIGO and Virgo, the phase of the signal can actually, well, the old signal, let's say, the phase of the signal can actually be decomposed and as basically a sum of two contributions: the point particle contribution and the tidal contribution. Now, the point particle contribution basically depends on mass parameters. For example, this eta is a combination of the masses, and this is the total masses. Okay, this is the frequency, and then in this region here, there will also be, for example, the spins of the two compact objects. Now, I've written here the phase of the signal in the way that we will build the templates in gravitational wave astronomy, which is through this thing which is called post-Newtonian expansion. Okay, it's not very important like the technology, but this is just basically a speed of 1 over speed of light expansion from something which is called the Newtonian term. Okay, basically this term 1, the 1 is basically the quadrupole approximation that Einstein derived in probably 716. Okay, and then people have computed the different orders of approximation in this expansion, and each 1 over c squared terms count as a 1 post-Newtonian term. So this is 1 point post-Newtonian, this is 1.5 until the 3.5 pm. It's super difficult to compute these terms up to a certain point. I think now they are known up to the 4 pm, and then it becomes really prohibitive, I mean, to analytically to compute these things. But there is one important thing, is that at different orders, there are different parameters counted. Okay, for example, like you see that the one of the combination of the masses appears at the 1 pm order, and then the spins, I think, also appears like at the 1 or 1.5, I don't remember exactly. Okay, and this is the point particle term. And then there is the tidal term, which depends on the masses, but also on the log numbers. In principle, there are two objects, so there are two log numbers, okay, of the two stars. Okay, and okay, the parameter that in general you measure the best is actually a combination of these two parameters, this lambda, that is called the average log number or the average tidal deformability. Okay. Now, I put this thing of the post-Newtonian expansion, not too much for the technicality, but because there is a very important point, is that if you look at the tidal phase, compared to the 1, this enters with a factor which is 1 over 10. Okay, this is in principle, so this is 1 over the speed of light power 10. So you may ask why. I mean, we should consider something which is 1 over 300 kilometers per second at the power of 10. This is because the log number is extremely big. So these lambda are order of 10 to 4, which also makes the entire contribution comparable to this terms here in the series. Okay, so even if formally in this Taylor expansion, this guy here is very small, even compared to the most accurate thing that you have here, but the overall contribution, because the log number is 10 to 4, becomes then comparable to this thing. So it's not only important because there is physics inside and you want to extract this physics, but it's also important because at some point it may become a sort of systematic effect, especially for next generation detector. Because basically you have a term here which is comparable with something here, and you don't want that your mismodeling or the fact that you are neglecting some term actually affect also your imagination. All right, and okay, what I've been saying here, very that looks a bit generic, actually I've been realizing practice. So basically, we got GV170817, and LIGO and Virgo actually measure these log numbers. Okay, and this is basically, again, this lambda tilde is basically this guy here, so the average. Oops, sorry. Okay, so this is the measurement from the first the first binary electrostar observation, and this is basically a contour plot in the lambda1, lambda2 plane. Now, these are the lambda, the log number divided by the mass of the object power of 5. This is why you see that the numbers that they find is not 10 to 4, but order of 200, 300. Okay, you have to divide that 10 to 4 by the mass of the star to power of 5. Okay, so that's why it becomes, but it's the same. And what this plot tells you, basically tells you, you see, this is the region with the highest probability of the measurements. And here there are different equational states, okay? And if you see the arrow indeed is going more compact, of course, go to the 0 because the log number are smaller, less compact are in this region here. And you see the higher probability distribution is basically pointing in the direction of more compact equational state, okay? So it seems that the first binary neutron star event suggests that we have soft equational state in nature, so ruling out stiff equational state. All right, okay, this is basically, if you want to translate, then you want to go from macro to micro, the measurement of the log numbers can actually be translated into measurement of the mass and the radius, and this is indeed like these are the two basically neutron star of GP17 or A17 in the mass radius, and this radius basically has been obtained mapping back the log number to the radius, and these are like some equations. So you can basically also go back to your favorite mass radius curve if you wish, and then these constraints on the log number also can be translated into an equation on the constraint in the microphysics. So basically, this is again the pressure density relation that you will get after the observation. Okay, and indeed these are the values of the radii that we found. Okay, now I'm actually gonna give you a bit of instead like ideas on what you can do with these measurements, and this in particular is like a project and a work that we did with Costantino Pacilio, and was postdoc in Rome with me, and also with Paolo Pani at the time, and Margherita Fasano. So basically, the idea that we try to answer, or actually to develop, and the question that we try to answer is, okay, there are many equational states, but can we actually try to create a framework in which we can actually ranking the log number? So take like this ensemble equational state, there are actually order of 10, even more, 20, and basically can actually give a number for a given observation that tells this is the most probable, that's the least probable, the second most probable, and blah, blah, blah. And actually you can do this doing like some some like Bayesian basically analysis. And indeed, like Costantino in particular developed this hierarchical Bayesian test. So basically, in which what you do basically is like you have the evidence, so the probability of a given observation. So this T could be the log numbers of like and the masses of GP17 or A17, and you compute the evidence of getting these log numbers and mass given an observation for an equational state. You compare this for another equational state, and then you see basically compute the bias factor, and you basically see which one is more favorable with respect to the other. We took, for example, this ensemble of equational state, this set, and there are different names, and these different equational states differ each other because of the way that they describe the nuclear interaction in the inner core. This label stands, for example, for nuclear many-body theory, or relativistic mean field theory, or relativistic field theory plus the confined quark described with a certain Berg model and blah, blah, blah. And this particular way to describe the equational state also translates in different particle compositions. So you see nuclear clock of electron, muon plus hyperon, or quark matter, and blah, blah, blah. So the way was, the question was, okay, we have one observation and we try to rank all these in order to see whether we can actually distinguish equational state computed with different methodology and different particle content. And of course, when you have the base factor, there is like a certain scale which tells you whether basically one EOS is decisively disfavored or favored with respect to another one, or strongly. I mean, it's, I don't remember which name, the name is the Ratti scale or something like this. Okay, and this was basically applied, for example, this was just a game in the sense that it was applied to the first event, which was the first event, so it was super useful, but okay, with a limited constraining power, but still, I mean, it was just to show the feasibility of this model. So basically, again, this is the the logarithm of the bias factor, normalize basically to the equational state with the largest evidence. So basically these bars tells you whether basically these equational state are favored or disfavored compared to this one, okay, which is the most favorable in the catalog, which is also like the softest one in accordance with the measurement. So the one that predicts very, very dense models. And indeed, this basically tells you that for a measurement with the accuracy of the GD17 or 817, the majority of the equational state, if you make the ratio of the bias factor, are more or less like this. So you cannot claim a lot because they are below the strong basically bias factor scale. There are a couple in which more or less like the evidence is in favor of this guy here. Okay, the only real disfavored one are these two, which are actually the stiffest equational states of the catalog. Okay, okay, I don't want. Okay, so basically, which again it's compatible with what we saw from the plot of the measurement of lambda, which tells you that you cannot really basically the only real thing that Virgo was doing is like ruling out very fluffier equational state. All right, and at this point, we asked exactly this. So at that time, say, okay, in the future, maybe with O4 and I don't know, yeah, O5 as well, maybe we'll get more help in the sense that this framework also allows to stack events. So maybe if you combine together different binary neutron star observation, okay, we haven't observed anything, but in principle, you actually do better. Can you? Well, it really depends on what nature has actually put inside the stellar cores. Because what we did here, we simulated like 20 neutron star observations, not even too far, between 20 and 200 megaparsec. Okay, and so observed by Virgo. Okay, so we said, okay, let's do basically the GD170817 simulated observation. Okay, in which we have these 20 neutron stars. And we inject a neutron star into the gravitational noise, into the detector noise with a given equational state, which is a stiff equational state. And we try to see, okay, if we can discriminate the signals from other signals built with different equational states. So we do this ranking, so we compute the bias factor again, but with a simulated event in which the injected guy is a stiff equational state. And you see basically that if the equational state that matter measure has put into the neutron star is really stiff, you can actually discriminate kind of decisively each equational state from each other, and in particular, more or less after 10 observations all stacked together. Basically, you can discriminate, you can say, okay, my equational state is stiff, and I can rule out all the soft equational state. Okay. Unfortunately, if Mother Nature has put a soft equational state, as actually appears to say, again, soft equational state means more compact neutron star, which also means that the log number is smaller, so it's more difficult to dig out log numbers from the data because it's a smaller number by definition. And in this case, you see that while basically in this case the bias factor was immediately dropping into the decisive, so basically saying, okay, I can actually discriminate half-2 with all the others. In this case, it doesn't happen. Okay, even stacking together basically a lot of up to 20 observations, the majority of things cluster in this non-decisive basically region. There is only basically this guy here which is dropping, which is an equational state which is very, very different from this guy here, which is a soft equational state and now we injected. So basically these things tell you that for with Drag and Virgo, even if you stack together like order of 20, 30 observation, it's very difficult to discriminate two equational states unless they are very, very different in stiffness. Okay, if they are close, there's no way to do it. Or it's very, very difficult. Okay, but at this point, we try to get information on whether this thing could be done with the next generation detector, so the Einstein telescope. And before doing this, probably it's worth like saying which is the accuracy that you would get with the Einstein telescope on the measure of the log numbers. Now, I'm sorry to do this thing, I forgot to put a label, but if you remember this number, so the constraint that LIGO has put of the log number are the order 200 plus minus, let's say 100, okay? Or 600 plus minus, okay, this is even like order of hundreds, okay? Now, if you go on the projected constraints on with the Einstein telescope. This is basically a study that tells you the uncertainty on the log number as a function of the total mass of the binary for different well, Einstein telescope configuration, but they are mostly the same. And you can see that in particular in this region here, more or less, you can get order of 50 up to 10 the error on the log number. So basically, you can beat easily of 1 order of magnitude the uncertainty that you will get, that we got with the GV17 or 817. Okay, this in principle should allow to distinguish easily, not easily, but I mean more comfortably, like a question of state with different content. And indeed, when we applied basically what was like our approach of ranking like a question of state with the Einstein telescope, this is basically what we found. So again, now we create again this set of 20 injected observation. Again, we consider the pessimistic scenario in which we inject the soft equation of state, so the one which is difficult to discriminate from the other one. And you see now that basically the majority of these are actually, the majority of the equation of state actually provides bias factor, which is when you don't see the bar, basically means that is 10 to minus 5, 10 to minus 6. So they are basically completely ruled out. So basically the idea is that Einstein telescope is so powerful that the majority of the case can actually discriminate any equation of state from the other. And even if there are two equation of state which are very, very similar to each other, okay, if you combine just 2, 3 events, you'll be able basically to rule out or at least to distinguish that particular equation of state from a convector. Okay, so the idea is that while LIGO and Virgo cannot really do anything special if the equation of state are very, very similar in the particle content, instead with the Einstein telescope you can, okay, and like a bunch of these observations will basically do the game. And so basically will be in principle able to, will be in principle allow you to distinguish things which contain different particles inside the neutron star. Okay, this is really doing fundamental physics with the Einstein telescope. Okay, of course, this was like, everyone knows that basically GV17 or 817 was also the golden binary, also because was the, okay, people doing neutrinos maybe won't be in agreement, but at least the era of multi-messenger in the gravitational wave electromagnetic band, and there is tons of papers. I mean, I really, but basically people did everything possible with the log number, only 5 minutes. Okay, with the log numbers and other stuff. So, for example, using maximum mass constraints, like information coming from the kilonova ejecta from the gamma ray burst. And what I want to actually point out is the measurements that were actually done in multi-messenger to NICER. So in 2019, NICER basically got the pulsar measurement, well, the measurement of these pulsar. Basically, there were 2 groups analyzing independently, but I guess part of the same collaboration. So, I mean, they analyzed basically the same NICER data, and they come up basically from measurements, I would say, in agreement from the same pulsar. And this is basically, they measure the mass and the radius. So these are like the values of the 2 measurements. And so what people did in this case with this high quality measurement was basically to mix the data coming from the GV17 or 817 with data coming from NICER. And let me rush a bit. So actually even more. So for example, in this paper by Philip Landry and other people at Caltech, what they really do is do basically multi-messenger at its best. So basically they took, at the time there was also like the second binary crossover event measured, after the significance of, in terms of constraining the equation of state was very low. And so basically they basically use this catalog here, then the NICER measurement, and then the measurement of very massive pulsars that we got from different observations at the time. And here you see basically how these different colors basically are pressure energy density relation here if you combine different catalogs or set of observation together. And here, for example, you see the mass and radius curve profile. If, for example, you have I don't know, like this, the green one here is pulsar plus gravitational wave, and there should be like the tightest one, like this hard blue, is pulsar gravitational wave plus like the maximum mass constraint. And some like a plot that they put into the paper, which is I think is very, very explicative, is basically what you get from the mass and radius of the observed event before and after you mix together all the ingredients. So basically the dashed curves that you see here are basically the measurement of the first mass of GV170817, the second mass of GV170817, or of the NICER pulsar, before stacking together all the data sets. So these were daily independent measurements. Okay, when you stack all together, you basically see how the constraints improve and actually the parameter space actually reduces. Okay, all right. Do I have more time? 2-3 minutes to? Okay. The last thing that I want to tell is something that we did with Omar Benar in La Sapienza, and which actually was this is really, I think it's really like sort of fundamental physics, because something that we try to get from this is, if you think about the log number, it's really a sort of an average measurement. It's like basically the radius. So if you take the radius, it's an integral, okay? It really doesn't tell you too much about internal, what is happening at the level of nuclear interaction, okay? Because it's an average quantity. Okay, so the question that we asked, Omar and Andrea Sabatucci, that was a PhD student at that time in nuclear physics, was, okay, can we actually try to use the log numbers to constrain something dynamical, and in particular, the nucleon-nucleon interaction directly from the measure of the log numbers? And in particular, actually from multi-message observation. And in particular, we're interested to what is really unconstrained, which are like the strength of 3 nucleon forces. And in particular, we took an equation of state, which basically is a model to describe like nucleon interaction into the neutron star core. And basically, if you take like this, well, this is the Hamiltonian of the system, but basically if you have nucleons interacting, there is basically a two-body potential that tells you how like these two body interacts, and then there is a 3-body potential that basically tells you actually the interaction between 3 of these nucleons. Okay, if you go to a nuclear physicist and you ask how this thing is done, at least in this model, basically there is like an analytical part here, which is given by some Feynman diagrams, plus there is a 3-body potential, which is purely phenomenological. And what we did, basically, we parameterized this guy in terms of an amplitude, okay? And we say, okay, can we actually constrain this amplitude here, which is 1 in the reference model? And if we let them free to vary within the data, can we actually see if the data are sensitive directly to 3-body forces that we parameterize in this way? Note that in general, 3-body nuclear forces are not very constrained even on Earth, because there are very, very few systems in which this can be measured. And unlike what people believe, like if you actually tweak a bit the equation of state, you can change a lot your mass radius curve or your mass log number profiles. And indeed, these curves here tells you what happens to the mass radius profiles if you vary that alpha that I showed you before from the 1, which is the baseline model, to like different values. So from alpha equal 2 to alpha equal to 0.7. Okay, that alpha equal 1 is not like set there by nature. It's something that has some constraint from nature, but it's not very well constrained. Okay, so we are allowed basically to go from one place to the other. And this is basically what we did at the time. So basically, we took again a multi-messenger set of data with GV170817, and then actually NICER in 2021 put the radius measurement also of another pulsar. At that time, it was like the most massive pulsar. I think there is another one now, which is even more massive. And these are basically the constraint. If you just look at the left-hand side, these are basically the constraint on the strength of the 3-body forces with the different sources. For example, the red is basically the median of the distribution, and then this is the 90% confidence interval. And you see, for example, this is the values of alpha that you get from GV170817, the only binary neutron star. These are the 2 that comes from NICER. And if you start joining together all for example, these are the 2 NICER pulsar, GV and 1 NICER, and blah, blah, blah. And this is the old data set. Interestingly, at that time, what we found is that the 2 NICER pulsar are perfectly, basically, complementary. So they predict alpha, which is in like some similar values. But GV17 actually is pushing, and actually the NICER measurement actually pushing for values of alpha different from 1 from the baseline, suggesting that there are stronger three-body interactions in the nuclear, between nucleons and nucleons. And binary neutron star events instead is suggesting the opposite. So this is something that could actually be explored further. And okay, you may actually ask what, like as a last slide, what you could do on this particular problem, which again, this is a toy model mostly of fundamental physics. So really how to look into fundamental forces with the neutron stars, and in particular with the Einstein telescope. And again, here we did a simulated game in which basically we used the Einstein telescope with 20 or 30, I can count here, like observations. So we simulated again neutron star with different chirp masses, which basically means different masses, and with different luminosity distance, which also means basically different signal to noise ratio that you see on the top. And we injected a signal, which means basically neutron star with a certain value of alpha. For example, we choose first to select a neutron star with alpha equal 1, okay? And we try to constrain these parameters, and you see actually the goodness of the constraint that you get. Okay, and if you also, we made a second run of basically simulated injections with different values of alpha, and you see that not only like some of the observations are really tight, but can only in principle you can distinguish basically different values of alpha. So in principle you can distinguish different values of three-body interactions. Okay, I ran a bit on this, so you can ask me later if you're really interested, and I think I'll just can close on this. I don't like summaries.
Okay. So there are some questions?
When you try to constrain this alpha parameter, is it in the framework of a specific equation of state?
Yes, this is in the framework of a specific equation of state. Yeah, you have to do it necessarily.
So changing the equation of state, you could have different.
Absolutely, and this is why actually we did also the ranking, because we wanted really to tell people. I mean, if you do this equation of state by equation of state, you're actually able to rule out models. So the log numbers can mostly tell you the stiffness. So it's very good. I mean, if you want to do physics, you have to choose a model anyway, eventually rule out. And this is one of the ways. It actually could actually be, for example, this is consistency, just tells you that the model is not appropriate. Because here for the measurement of alpha that we got, okay, the uncertainties are still large, but seems to suggest that, for example, Neisser was predicting a value of alpha, which is this, and the UD17 a value which is this, which may actually be that the model that we are using is not appropriate to describe. So this actually can be not only interesting for the measurements, but you have like one parameter that can actually be used in, let me say, redundancy test between different observations.
There's Oscar online.
Oscar, yeah. Could you hear me? Okay.
Yeah.
Thank you. I have several questions, of course, but I limit to one probably. So when you talk about, since you have, as you have shown in the second or third slide, that there is a stratification, no? Inner core, outer core, crust, and so on. When you refer to the equation of state, you are referring to the inner core, just to the inner core, so the most dense part of the neutron star?
I would say that, so for me, specifically, the equation of state is like means the way that you model like well, I would say like strong interactions that could actually be translated like in P equal P. So the real like the equation of states that you basically like with familiarity to thermodynamics. So P are these pressure density relations. I would say you can think just of the inner core because there is a general agreement between the lower part, so actually the lowest density part. So the equation of state is everything in the neutron star.
Yes, of course, but since I don't know, Hyperon may forms just the innermost part.
Yeah, absolutely. So, like since there is more agreement like in the low density part, we can the problem of the equation of state is mostly like in the inner core. But let me also add that in the last years, also people pointed out that the small differences that, for example, are in the theoretical models that predict like the lower density composition may actually not be too small for next generation detectors. And this is actually something that we need to take into account, in the sense that agreement or not agreement, if you have a theory to predict observables, it also depends on the accuracy with which you measure that particular observable. So, for example, the Einstein telescope may be so sensitive that even the small deviation that you have in the outer core or in the mantle basically may actually be sort of systematic, so actually may be disentangled by measurement of the Einstein telescope.
Okay.
I don't know if this is clear.
Okay. Could I do another question? Okay. Okay. So sorry, but I'm a little bit biased by my experience. So we know two ways to form a neutron star. One is the classical one of a massive star that evolved up to the silicon burning, form an iron core that collapse, eventually giving rise to a supernova. And the second one is the accretion-induced collapse, in which you have a massive white dwarf, an oxygen neon, in a closed binary, relatively closed binary, that accrete matters until the Chandrasekhar mass and then undergo a collapse. There are two main differences in between these two, the resulting collapse. In the first case, you may have different masses, practically from the Chandrasekhar mass up to the upper limits for stable neutron stars.
Yeah.
And the composition of the collapsing core is iron-rich, and this means that you have an excess of neutrons with respect to protons, because this is typical of iron. While in the second case, in the latter case, you have oxygen neon, and the mass is close to the Chandrasekhar mass. Of course, the resulting neutron star have a smaller mass because of the loss of energy, of gravitational energy during the collapse. But by the way, the mass of the resulting neutron star is very confined, and the composition of the collapsing core is the YE exactly 0.5, so same number of neutrons and protons. So the question is, these differences may have an effect on the equation of state of the resulting neutron stars. Sorry for the long.
I'm not sure that I got completely everything, but I'm not a stellar evolution person by definition. But I think that the point is that
so during the collapse, protons are converted by electron capture into neutrons. But so maybe that this process cancel any difference in the chemical composition of the collapsing core. So that the question essentially is that
so,
there is some reminiscence of the original composition or not. That could be interesting.
I don't know exactly how to answer this. The only that, I mean, something that I can answer is that it seems that it's I don't know how to put it, but the difference is like, okay, without looking at this, okay, which something that I'm not able, at least at the moment, to relate is at which densities this process actually play a role. Because something that I know is that above one nuclear saturation density, we basically don't have any real clue of what is happening between like nucleons, or like there are ideas, but nobody knows. So if you have two stars and like I have one star of one solar masses and one of two solar masses or 1.5 solar masses, they will have like a central density which can go from 5 to 1 nuclear saturation density. And it's very difficult at the moment at theoretical level to tell you what's happening between two stars which have 1.5 solar masses and 2 solar mass of total mass, because they have a core of 5 and 1 nuclear saturation density as central value, because nobody knows what's happening, like which are the particles that are forming. So that I think that different channels leading to different masses means basically objects with different central densities or different inner cores. And the answer, at least from a theoretical perspective I can give you, is that there are no models that really tells you univocally which happens there. So two different channels predicting two stars which are more or less dense have differences because nobody knows what's inside.
Okay, thanks.
In the last part, you showed that you're modeling by using three-body forces.
Yeah.
Are there any plans to model with n greater than 3? For example,
no, it shouldn't be. I mean, already three-body forces is it's because basically you are at that kind of density. Actually, no, three-body. Let's put it this way: three-body forces should be enough to model the interaction. And as Omar, who is a nuclear physicist, was always telling me. Of course, I mean, like the fact that this nucleon forces plays a role, which is kind of unlikely from different systems that we observe in nature, is because of this extreme density. But there is also a very nice way to see this in a classical level, is because at that density, which means at that energy, the nucleons are not anymore like the fundamental degrees of freedom, in the sense you can see this as a structure with something inside. And so basically what we're actually observing are tidal forces, because these objects are not anymore point-like, but the nucleons is actually made by quarks, so it has a finite size. And so like in the three-body problem, basically you see that there are like these tidal forces acting on that density of something which is not anymore fundamental. There are something more fundamental, which are the quarks inside the nucleons. But the idea is that three-body forces should be enough to model the
Okay.
There is one question by him.
I need to swim in waters when I feel more comfortable. So, no, I just from the astrophysical perspective, first of all, I had no idea about NICER. I had to Google it.
Oh.
So, if you can say some words about NICER. And the other thing is, you also mentioned from the electromagnetic perspective, you mentioned low mass X-ray dynamics. I don't know if you can say something about it.
Yeah, my mother always tells me that I speak too much.
No.
So NICER.
No,
I can say something. So NICER was this it's running and is doing measurements of hotspots into. And I don't want to say millisecond parser, but this must be a millisecond parser. Let me take full responsibility for this. So these are like hotspots from millisecond pulsar. There is, I mean, you need to model the hotspot and the geometry of the star in relativity. It's an incredible mess. And I think that the real measurement they are not part of the experiments. I think that the real measurement they make is basically the redshift, the surface redshift, and then from which they are able to extract the mass and the radius of. And this is basically what they do. The two different collaboration, not always I would say in agreement, put out as a result. Let's say that within the errors they are compatible. For let me say for the other where did I wrote this? Okay, low mass X-ray bias, I probably said it. It was probably a bias from, I think I was probably mentioning a paper that I did with some years ago with Sara Motta, Luigi Stella, George Pappas, and other people, in which basically, okay, that's a speculation of speculation. I'm violating the Matt-Visser rule. I'm not introducing two speculative things at the same time. So basically, there are these QPO in low mass X-ray binaries, and this quasi-periodic oscillation in the X-ray fluxes emitted by this object. And there are models, but at least some of these seems to predict that, or at least they model like this variability in terms of geodesic motion of particles, not particle, blob of matter. So there is a blob of matter into the accretion disk. It moves and it oscillates. Okay, and this oscillation basically ignites this variability. Now, the point is that in general relativity, basically, the motion of the particle outside is also determined by the quadrupolar, by the multiple moments of the central object. Okay, so if it's an astrostar, the multiple moments of the star will actually determine how the object move, and in particular the quadrupole moment, and the spin-induced quadrupole moment. And the spinning-induced quadrupole moment depends on the equation of state. So the thing was to use this variability of observing X-ray spectra use this model that depends on like test particle or like a motion of blobs of matter to connect the frequency, the modulation of the frequency with this motion. And since this motion depends on the quadrupole moment, which depends on the equation of state, then do all the chain from measurements of this variability to quadrupole moment to equation. But I mean, it was a proposal.
And I think we can thank everyone.
Let me to be